Hello and welcome to another one of these ADD videos. Today we're going to look at the concept of resonance. What is resonance? Well, sometimes when you're drawing Lewis structures, you can have multiple valid Lewis structures of the same molecule. Well, when we have these multiple Lewis structures, they lead to unexpected bond energies and bond lengths, right? We know the length of a single bond and a double bond between a carbon and oxygen, for instance. And the main difference between these resonance or structures or these valid Lewis structures is the placement of these electrons, okay? So let's take a look at this example here. If you see R just means it's a carbon chain of some sort. Okay, so for instance, if that was a CH3, this would be the acetate ion. Okay, but let's just call it R for now. Whenever we were looking at this experimentally, we would expect to see two distinct carbon-oxygen bond lengths, one for the single bond here, and the other one for the double bond there. But in actuality, we don't see these two different ones. What we see is two carbon-oxygen bonds that are exactly the same length. How can this be explained? Well, this can be explained if the pi electrons were shared equally between both oxygens in that structure. So here, if these two guys shared them equally. So let's look at what that would be like. So this can be also referred to as resonance forms or resonance structures. Don't be confused if you see one or the other. But this is the interchanging of the negative charge. Sometimes it's up here, sometimes it's down here. Okay. So what we can do is we can write this as a combined thing called the resonance hybrid. And this resonance hybrid is easily represented by drawing a dashed line between the two elements that are sharing those pi electrons. And note that the -1 charge that was here and then switched to here is now shared equally between these two oxygens, therefore making this ion more stable. So there's your resonance hybrid. All right. In some scenarios, the resonance occurs between elements that are different, not two oxygens. In such a scenario, you have what are called major and minor contributors. And the major contributors will be more stable and more closely resemble that real molecule. The major contributor will tend to have more full octets than the minor. Negative charges will be placed on elements that are more electronegative, such as oxygen. There will be no charge separation or little charge separation in the major contributor. And then we can have positive charges on elements like nitrogen. Even though it's an ion, there are many stable elements or compounds that have nitrogen with a plus charge on it. Minor contributors will have unfilled octets, charges on carbons, charge separation. All these things are undesirable, make it unstable. So the major contributor will have a higher percentage over the minor contributor. You'll see it more often than you will see the minor contributor too. The actual resonance hybrid. So what are the rules for drawing these resonance structures? Well, the first rule is that it must be a valid Lewis structure. And if you don't remember your rules for Lewis structures, go back and review them, please. The next rule is that you can only move electrons to adjacent structures. No nuclei can move. No elements can move. You have to preserve the bond angles. So a lone pair can move to an adjacent pi bond or empty p orbital to form a pi bond, or a pi bond electron pair can go to a lone pair. Okay, that's the second rule. And the third rule is the number of lone pairs must always remain constant. They must never change. If you can do that, then you can successfully draw resonance structures. I've given you the rules for major versus minor. Just practice a few of those. And you will be familiar with resonance. I suggest that you become very familiar with resonance because resonance will come into play throughout this year. Resonance confers stability and is a key feature of a lot of reactions and determining reactivity of different things. So please practice drawing resonance structures. Make sure you check out the example videos for drawing resonance structures, and we'll talk about it also when we're dealing with acidity, what makes a stronger acid, and you will see that resonance definitely plays a key role in making acids stronger. Reason being, whenever you donate, let's look at the acetic acid that we were talking about earlier. Or actually, I gave you a general acetate ion, right? But okay, if we stick a hydrogen on the oxygen that had the single bond, this now becomes acetic acid, right? Hopefully you know that. If not, you will soon enough. Just start learning. So this acetic acid, once it drops that proton, has the scenario we just witnessed of having the resonance hybrid. And what happens now is that this is extremely stable as an ion because the charge has now been split in half and is being shared by the, oops, that's a delta, not a D, 2 oxygens. So that would increase its acidity, all right? We'll talk about that later on as well. So I hope we've cleared up any confusion you might have on resonance structures. Please check out the example videos. Practice, practice, practice. Thank you and have a nice day.